Hello, I'm Renzo Huber, and today I want to show you the entire Layer-fMRI analysis pipeline in a tutorial. Basically, I want to show you on my Mac how you can take raw data from the scanner, convert them to Nifty, do a motion correction, do the layerification, and extract your layer profiles. I will work on this dataset, which is available on the Harvard Dataverse. I will post the link also in the video description below. And this is an example that has been used in other tutorials already, for example, for structural reference data. It has BOLD and VASO included. It is a 7 Tesla dataset with a flickering checkerboard task. So you can download it from the Harvard Dataverse, and you can see that there are different folders in there. We will specifically look at the functional data here, at these different time series over here. You can download it by access dataset and download the zip file, which I already prepared. I will use a number of different programs here. First, I will use the LayNii program. So this is developed by Farouk Gulban and myself, and you can look at the references over here. You can download it from GitHub. Next, I also use AFNI here and there. And you can install AFNI, for example, by simply downloading the binaries, precompiled binaries. I'm working on Mac, but anything here should work on Linux just as well. So I will use a vanilla version of AFNI, of just using the command line programs without the fancier things that depend on other things. For visualization, I will use ITK Snap, which you can download at this link. It's very easy to install. And we will also use this for manual segmentations to ultimately then do the layerification. And this is an optional part of the analysis pipeline. It's Nordic. It's a denoising step that you can do, but don't have to do. And some people are skeptical, and some people find it very, very useful. I want to show you just how this is done in VASO and BOLD. Layer-fMRI. If you want to use this thing as well, Nordic, you can download it from Steenmöller's GitHub over here, and this is dependent on MATLAB. So you need to have MATLAB installed as well. Okay, then we can go to the actual data that I already downloaded. You can see that there are different subfolders. We will go only through a subset of them. You can, for example, only look at the BOLD data if you want. You can look at the VASO and BOLD data, which is what I'm going to do today. There are structural reference data, but also distortion match reference data, which I described in another tutorial. We will first convert DICOMs to Nifty, then do the motion correction, BOLD correction, before we can go to the layerification and the layer statistics. So when you acquired your data from the scanner, usually you have them in DICOM format, which is shown here in this example. Depending on how the scanner is configured, you might have the DICOMs in a gigantic overarching folder that has all the DICOMs from the entire session, or the scanner nicely splits them out into the different series. It doesn't really matter for the purpose of how we do the conversion over here. In this specific case, we have the subfolders, and then there's a DICOM folder within there, and then we have the multiple DICOMs within that subfolder. So we can start by converting this and then have a quick look at the data as well. So let's look at the conversion script, which in this case, I'm using the DCM to NIRX, which is a program that's very popular and developed by Chris Rorden. In order to execute this, first I need to go into the respective folder. And then I need to generate a subfolder where all the Nifty images then can be dumped into. So now we have this little subfolder Nifty that is still empty. After that, you can run a big loop that's basically looking through all the other folders in here and then trying to find all the DICOMs within those subfolders and dump them into the Nifty subfolder that we just generated. And you can see how this works. Here it's going through the different series. And you can see it's spitting out a lot of series already and dumping them into this folder. And you see that it follows a certain naming convention, which is defined by this here. It starts with an S, and then we give it the series name, and also we give it the indications of which echo time it is. This is a single echo experiment, so we only have 0 zeros here. We have multiple sets, though. Namely, we have S00 and S01, which are referring to BOLD and VASO, respectively. But also we have these capital M and capital P's, which are referring to magnitude data and phase data. So if you look at one of them, you can see that this would be a VASO data, S00. It has an inversion recovery contrast. CSF is very, very bright on the first image. and it's a magnitude image. Some people like phase data as well. So here, for example, people use phase data, for example, for denoising purposes or for detecting specific veins or gray matter, white matter segmentation. They're all included here, but we will ignore the phase data for now. If you're interested to see how this not looks for vaso, but maybe for bold, here this is maybe the more conventional contrast that people are used to in fMRI. You can also see the kind of the coverage here. We have a SLAP data set around the visual cortex. Additionally, we also have these JSON files that are giving you the kind of meta information of these runs. Specifically tells you that this was acquired at NIH at 7 Tesla with a 32-channel Nova coil and so on. So now that we have all these data over here, we can have a quick look at them. And for that, I have a few commands prepared over here. So we can first go into the data folder and then see how we would run this a little quick look in Nifty. So for example, whenever you run a LayNii program, you can use the -help option and it tells you how you can use it. This is ln_info, which basically tells you can give it an input data set and then it will show you some of the overarching kind of structure of the data. And you can even look at it in a terminal real quick. So for example, if I give it this input, you can see that it tells me how many voxels I have in the X and Y direction, how many slices and how many time points. And then it also tells you kind of something about the data type, which would be also here integer 16. If you click enter, you can actually also with little ASCII in the terminal directly see kind of that this is a brain image, it's axial, if you didn't know. So now we know how to look at the data and we know where they are. We can basically select the data that we care about for further analysis. For further analysis, however, it might make sense to follow the bit standard as much as we can. And this naming convention that I just explained is not really bits compatible. Specifically in bits, magnitude should be described as the word magnitude. Bold and vaso should be described as _CBV or _bold respectively. So in the conversion script, over here, there's a little script as well that tells you how you can kind of rename anything that's called S00 to _CBV. So I can basically copy paste this thing in that folder, and then you will see that now my data are renamed. And then I can grab the data and put them into a specific folder that I want to analyze next. So specifically, I'm interested in all the runs in AP direction, not the PA, which some people might use for distortion correction. So everything that has a run in there and is a magnitude is something that I'm interested in. So I'm selecting all those and copy pasting them into the subfolder where I'm doing the denoising, the motion correction, and the bold correction. And I already have them here ready. So those are the data, bold, vaso, bold, vaso, bold, vaso. And you can see that for each run, we have two data sets, bold and vaso, which are acquired concomitantly. So now that we have all these data ready, we can start with the first step, which would be the optional denoising with Nordic, which I run the commands that are in the 00 Nordic SH script. So you can see that it's basically looking for all the data sets in that folder that start with S and end with nifty GZ. And then it's executing Nordic by calling MATLAB. This might be a path that might be different on your computer depending on which MATLAB you're using and where you installed MATLAB. It might certainly be easier, I think, in Linux, where it might be just MATLAB command, or it might be also different if you run this on a server, but it certainly relies on the Nordic wrapper script, and the Nordic wrapper script in turn relies on the nifty Nordic script. So we have all these three within the same folder. So I can either copy paste this into my terminal, or I can also just execute the entire script. And for that, I will first go to the respective folder that I'm in now, which would be this folder. And then I can run the script, which would be in the same very folder, 00_Nordic. So now you can see it finds the first nifty already. It starts with the VASO data, the CPV data, then it opens MATLAB. It tells you which arguments you're using in MATLAB, and I'm specifically using the arguments that have been found as useful from Lasse Knudsen in his paper of 3 Tesla Layer-fMRI VASO, where he compared many different versions of denoising for VASO data, slab selective VASO data. Specifically, here we are using a factor error that's bigger than 1, which is something you can get away with when you have kind of strong block design data, where the PCA that's using the denoising in Nordic is kind of very capable in separating thermal noise from these kind of block design models. Also here we are using the magnitude data only. You can use the phase data that we have as well if you want to. We are also estimating the G factor itself, so we are not using the fact that the last 2 TRs in the data sets that we have here are actually noise data. This will take a while, maybe 20 minutes or so, until all the 6 runs with both the contrast, bold, and VASO are completed. So now, a couple of minutes later, Nordic is completed, and you can see that it generated a number of MAT files where it gives you some output that is not of further interest to us. It also kind of overrode the file names that we had before, of still having VASO and bold interleaved with the same file name as before. So you can run the next step with or without Nordic, depending on how you want it. So next, what we want to do is the motion correction. And the motion correction is shown over here, which we can load in there. And there is some description in how this is done and why it is done in the script as well. The first part of the motion correction is basically finding a good mask to apply the motion correction in. So I copy paste this because I wanted to show you the in-between steps. So it is generating a little mask. And this is very helpful because for these kind of slab data that we're looking at here, very often the outermost slices are kind of tricky and have different signal magnitude. So maybe if I show you this in ITK Snap, you will see the problem a bit clearer as this is moving up. So here you can see that the outermost slices have fold-over artifacts and are kind of getting darker. Now, if you don't tell the motion correction about these features, it might actually confuse these outermost slices and the darkening at these outermost slices as a true signal contrast, and will try to align this kind of borderline there, which is counterproductive, right? Because we want to do the motion correction based on the brain, not based on the edges of the field of view. So this is something that has been optimized a lot by Paul Taylor and also Andrew Persichetti. So it's basically generating a mask of the brain and then also eroding the outermost slices of the brain, which is this series of commands over here. Then next, there are 2 big loops where I'm going through all the bold data separately. I'm defining my reference image, which is an image from the beginning of the first run that everything later will be aligned to. I'm getting rid of the very first TR and I'm overwriting it because the first TR is not yet in steady state. And certainly I'm also getting rid of the last 2 TRs. I'm starting counting at 0. That's why there's a 3 here. So I'm getting rid of the last 2 TRs because those TRs are noise data that can be used for Nordic if you want to. Maybe to give a better idea of where this is coming from, I can quickly look at LayNii, which is a little viewer that was added to LayNii recently. And we can, for example, take this VASO data set over here, we copy the file name, and then we can include the path over there. If you run LayNii the first time, it might be that kind of the alignment is slightly different depending on kind of how you have it set up. I'm adding this file name and then I'm loading the data. And it should take a second. So now you see that we have my data set here, and the first TR has this weird little kind of structural contrast. So if I go through time, you can see that later I'm in steady state, and you can also see that we don't have motion correction yet. So the brain is kind of moving downwards in the phase encoding direction, which might be due to temperature and frequency drifts. Certainly also the last 2 TRs are just noise. For example, when I look at any time point here, you might actually already see kind of the on and off structure of the task, slightly block design. And then the last time points are kind of jumping down, right? There's no signal over there. So the entire point of this line over here is to get rid of the very first and the last two time points. And then it's pumping this through the AFNI motion correction 3D Alineate, which is using the motion mask that we have created. And then it's using every run and aligning it to the first reference that we acquired at the beginning. And it starts everything with bold, and then it does the same thing for Vaso. And because there are a number of runs and there are two contrasts, this can easily take to half an hour, 40 minutes or so, which I'm going to execute now. So I'm typing in the script. This would be O1 Moko, which stands for motion correction, CBV, and bold. It does both, right? And so it's rerunning the outer mask that we already did. It's eroding the outermost slices, and then you can see that it's now starting to use the reference data and align the time series data to it. Where we are still in the 3D T-cut, which would be this part where we are taking care of the last and the first TRs. So now it does the alignment across the 200 TRs that we have. It starts with a coarse pass, and then it goes through every single TR in a second. So here you can see the first TR, the second TR, the third TR. So it is certainly faster in real time, but it still takes a while if you have very, very big data sets. So we can come back maybe in an hour or so. Okay, so now the motion correction is done. It took a while. And then I can look into what new data we have. So we have our original time series over here, and then this script generated a number of bold and CBV MoCo files. So for all of the 6 runs, starting from 100 to 105, we have the motion corrected data now. So if you kind of look at them, you should see as I'm going through the different runs here that they are roughly aligned, right? So you can see that specifically maybe in this sagittal view that kind of the brain seems to move quite a bit in the first 2 runs. However, it's the borderline that kind of moves. It's not the brain itself. So the motion correction seems to work. Things to watch out for with these lab data is sometimes when the slab is completely moving outside the field of view, which is usually something that AFNI is complaining about. This can be dealt with when you change your motion mask and make it more restrictive, reduce more slices on either end. So now that we did the motion correction, we can go to the next step, which would be the BOCO, which stands for bold correction. And here we are doing this across different runs. So first of all, as part of BOCO, we are getting the average of all the different runs, because in the bold correction, it makes more sense to do the bold correction on the high quality data than doing the bold correction on low quality data and averaging later. So it makes always more sense to, average first and then do the bold correction later, because the bold correction is literally an advanced version of dividing blood null data with not null data. Since bold and vaso are acquired in the same sequence alternatingly, they are not acquired perfectly synchronized. So therefore, they are kind of shifted by half the TR. In order to account for this, I'm upsampling bold and vaso with a factor of 2 across time, and then I'm shifting the bold by 1 time point. So now they are kind of in the same tempo grid. And after that, I'm running the bold correction, which is part of LayNii. And looking at the mean images of vaso, doing kind of background noise removal. And in order to start this, I can go here to my script. This would be O2 Voco. And you can see it start by averaging the different runs. While this is running, this might take about kind of 3-4 minutes or so. We can continue going through the different script here, because here I'm overwriting the TR in the header. This is sometimes needed when you want to do the function analysis later in the units of second. In 3D EPI, usually the Kubitis definition of TR is the time between repeated shots. So this would mean for 3D EPI, like in this experiment, that you have kind of a few tenths of milliseconds, which is not the volume TR that usually is referred to with fMRI sequences. So we need to tell it what the TR was. So after upsampling by a factor of 2, this would be our TR. I'm also running LN-SKU, which is a kind of QA program in LayNii. So you can kind of look at different TSNR on the noise, on the kind of average correlation across the entire field of view. It kind of gives you a feeling of conventional artifacts that we are usually encountering when we do high resolution fMRI. So while this is running, we can maybe look at the data again and see how the motion correction worked, specifically also within runs. And for this, maybe I'm again running the viewer LayNii Ida. And I maybe look at a motion corrected run, maybe one of those. I'm copying the file as with the path name, so I can include it here and then load the data. So here you can see that we have a similar data set as before. Now, as we go through time, here you can see that kind of it goes bright and dark and bright and dark and bright and dark. That's our task, right? You can see how the task induces these changes over here. When I hover over it, you can see a nice task design here as well. Maybe what you can also see is that we don't have this motion anymore, right? Before, the time series were kind of the brain was moving down due to phase drifts, and now this is not the case. You can also try to explore this a bit, for example, by enabling correlation. So here, as you move through the field of view, you can see kind of how much there's the weirdness, how much this is correlated across the entire brain. So for example, here, if I look at one of those time points in orange here, you can see that this seems to really correlate with most of the brain. There are some negative areas here that are kind of the opposite. And you can also see maybe that in the top of the brain, there are some sensory motor networks popping up, which might be sometimes useful to explore the data in this fashion. You also see, especially in fat, that we have these kind of stripy patterns over here. So whatever the artifact would be, we see that the fat decays in the phase encoding direction, which could be up, down, and we have these kind of low spatial frequency shading patterns that you sometimes see when you do very high resolution fMRI. Now that this is done, we can actually see what the program generated. So we see that the folder has been filled with all kind of additional data sets. For example, here you can see the stuff that has been generated as part of the QA program, the LN-SKU. For example, you do see, for example, the skew, the statistical values, which ideally should be relatively flat. We do see it's mostly flat. Maybe we have kind of a CSF in there, which might be a feature of non-steady state at the beginning. In the TSNR, you see that we are not in the thermal noise limited regime, but in the physiological noise limited regime, for example, by the fact that we have much lower TSNR in CSF. We do see that the visual cortex itself is reduced, which is due to the variance caused by the activation. For example, you can look at the standard deviation. We have a lot of standard deviation areas that are activated. And we see a bit more kind of noise stuff in the center over here, which might be just a G factor. The overall correlation is sometimes very helpful when it comes to artifacts. We do see weird things here. For example, these low spatial frequency patterns, but they are not a concern because they do seem to be in a low enough temporal frequency that they're not really affecting our TSNR and the sensitivity in the back of the brain. And there's the mean image, there's something like a local gradient, kurtosis, image SNR, and autocorrelation, and those kind of things in case you want to browse them. So now we have these data averaged across runs and in bold and in vaso. So now we can do functional analyses. And for the functional analyses, there are two scripts here. One is just a conventional GLM, and then we can also look at different kind of time courses as well. Maybe we start with the GLM here. which is using the AFNI program 3D deconvolve. And the task timing is shown over here in units of seconds. Basically, every 8 TRs, we have an on block that is 8 TRs long. So every 16 TRs, we have a complete trial of activation and rest. And this is doing it for Bold and then also for Vaso. It's using the output of these GLMs to also convert beta scores in units of percent. So we can run this now, which would be O3 activation GLM, which you can see that AFNI is being called now. It's doing the GLM for all the different voxels. It's writing out the bucket, meaning that it estimates the HRF, it estimates the T-scores, and it estimates the beta scores, which has been done. So next, what it does is doing the same thing with Vaso. So in the meantime, we can already prepare to look at that. For example, I might use the mean image of Vaso as an underlay, and I will open this in our viewer of ITK Snap. And you can see that it's kind of dark. In ITK Snap, you can increase the windowing by basically going right-click and going to the adjustment of the contrast. So next, let's load in the activation maps. For example, in Bold, we would have an activation map that would be the condition 2A. This would be Bold, so I'm loading this in as an additional image. I can overlay this. And now with the keys E and Q, I can change how transparent the images are, and I can also try to threshold this if I want to. Going to the contrast inspector, for example, doing everything from 4 to maybe 25, and maybe I'm also changing my color map to spring. So here you can see we have a lot of activity there, specifically back there in the brain where we would expect it. Now, if we want to compare this with Vaso, we can also include the Vaso, which would be the condition 1. And again, I'm loading this as additional image, as an overlay. So I don't need this anymore. I can change my color map and my contrast inspector also from maybe 4 to 15. So different than for Bold. If I close this, you can see that it's slightly more locally specific. We have the same overall area that's being activated, but importantly, we do see that we don't have these huge signals above the cortex. But in Vaso, it's kind of more sensitive to the signal within the gray matter. And maybe here we already know that we have the calculate sulcus over there, so we can already kind of decide which area we want to use later for our layerification. So maybe I would choose an area, something on one hemisphere right over there. Independent of that, you can also look at different ways of comparing Layer-fMRI profiles. For example, we could do something like looking at the early response versus the late response, which is something that can also be estimated in this little script over here, where I'm basically first doing averages of all the trials. And then within those averages, I can look at the early time points versus the late time points and extract the beta values for that. Here I'm using Bold only and basically looking at the early response and then looking at the post-stimulus response. So I can execute this as well. O3 activation and time early and late. So after this, we have multiple activation measures, for example, comparing Bold and Vaso, but then also we will have the different activation measures for early versus late. And we can look and see if we can extract a signal from those different measures of activity and see how the layer profiles are different. In order to do that, I'm grabbing my different condition files over here. And also for a structural reference, I'm grabbing the mean Vaso image as well. So I'm copy pasting that and putting this to the layerification. In order to define the layers on a very fine spatial grid, kind of smooth ideally, we would like to work on a finer spatial grid than the original resolution. And this can be done with the 04 underscore upsampled script. So you can see here that we are running this 3D resample command, which is an AFNI command, to upsample everything to 200 micron isotropic. Note, however, of course, that the native resolution is not higher, right? It just allows you to have less signal blurring and basically having smaller bins in the layer domain. So it's upsampling the structure and our four conditions, the two pairs of conditions, specifically the bold versus vaso, but also the early versus late. And we need to go to the layerification folder, and then we can execute this. And this upsampling takes seconds, simply because it really results in a much larger file types. So as we come here, we can see that it's already writing the first file. Now it might be complete and it's going over to the next one. So we can open this in ITK Snap to look at it, which takes a second. And then I can actually focus on the axial view over here. Maybe I can optimize my contrast, which was actually quite nice already. And maybe a good contrast is between 0 and 1. And we already have our area here that we care about, the part of the visual cortex back here. For segmentation, you can use multiple different programs. You can use FreeSurfer and then convert those surfaces into kind of volume space for LayNii, for example, with the Layer-fMRI toolbox from Marco Barilari. You can also use Zoomer for that to some degree, like other people did. Usually, you need to invest a lot of time in manual segmentations. So sometimes if you are interested in a small patch of the cortex, it's much easier to just do a manual segmentation. So for example, we know that this part of the cortex back here is activated. So as long as we see the gray matter, white matter border, maybe we can just go in there and then estimate our layers right in here. And you can do so by using this little brush over here. For example, circular with brush size 8 seems good enough. And then you can draw borderline where gray matter ends. And maybe I want to draw with label number 3, because that's often the convention in how this is done in LayNii later. So gray matter would be the value number 3. CSF would be value number 1. And then white matter would be value number 2. And I'm going through different slices here because ultimately this will always be estimated in 3D. While LayNii works with 2D data and even 1D data, to really, in the equivolume approach, estimate the right frame of the curvature, it very often makes more sense to segment a couple of slices. With the key S, you can kind of see the underlay. And then with the mouse wheel, you can kind of see how consistent you are across different slices. So maybe here it's already getting harder to differentiate gray matter from white matter. Maybe with the right mouse key, I need to actually undo some of the drawing here. Going down, and we can actually maybe elongate this here a tiny little bit. Further down, elongating this further. There are drawing tablets that allow you to make this kind of, to basically draw directly on the screen. Very often, I don't really bother, depending on how large the ROI is. Also, you need to be trained a bit on those drawing tablets as well. There are some wizards that do this very, very well. One of them would be for Gulban. There are tutorial videos on the Let's Analyze video series for LayNii, where he goes through this and his setup and the recommendations that he has for manual segmentations. I usually just take the mouse because it's fast and easy. And let's look at this in 3D a bit. Okay. We have a bit of jumping back and forth here. That's okay. The gray matter, white matter border doesn't seem to be jumping a lot. So I can now draw with label number 1, the CSF surface. I don't really care if CSF is kind of too big because it's only telling the algorithm which side gray matter is here. So I don't care if it's going too far in. I'm going through all the different slices and tell it where CSF is. Also, for the label number 2, which would be the white matter. And also note here that I'm only painting over the clear label. This means that I'm not drawing on anything that has been labeled already as gray matter. It can be quite helpful sometimes. All right. Okay, so we have our segmentations almost complete. And we can save this as our rim file, rim.nifty.gc. So now we can take these segmentations and convert them to layers. And this can be done in the script number 5 here. Basically this simple command. It's using LN2 layers. It's taking this rim file and estimating 10 layers with equivolume principle. So I'm copying, pasting this command over here. It always does equidistant first to get the streamlines. Then in the next step, it's doing the equivolume. It estimates the curvature as well. So there is this kind of iteration needed to estimate a smooth curvature for that matter. And now it's writing out the different layers, specifically with the file name rim layers equivol. So this is now what we want to look at and see if this makes sense. The equivolume approach maybe. So here, if I load this in as segmentation, you can see, okay, we have our different layers here. And you can then also maybe look at this in 3D if you really want to. So here you can see how the layers are kind of parallel, and you can see that we have a relatively small patch over here, but we are relatively consistent. So next, we can extract the signal from those layers. And this can be done by extract profiles. Specifically, there's the LN2 profile command, which is a LayNii command, and then you can extract the two conditions, VASO and bold, respectively. So it's basically looking at the binary classes of all the layers, and here we have the profile of an inverted U shape, which would be the VASO contrast. We have the x-axis would be the cortical depth, and the y-axis would be the magnitude, which in this case would be the estimates from the GLM. We can do the same thing for bold, and we can see how this is different. Specifically in bold, you can see that we very often have these superficial bias as usual. Now, while this little ASCII plot gives you a first impression already, and the real data are saved here in these text files where we have a table for each layer, giving you the value of the estimate and then giving you the standard deviation and then giving you the number of voxels you have for each layer, for that matter. For bold and VASO, and then we can also repeat the same thing for the two different contrasts if we want to. We can also try to plot this as well with a little 2D plot in AFNI, where you can see that bold really increases as we go to the cortical surface, and VASO and kind of has this inverted U shape, and even for maybe the uppermost layers, which is very few voxels only, so maybe not the most representative one, it even already gets negative. For the sake of completeness, let's also run the other two profiles here for the positive and the negative time points in bold. So in bold, usually you have these kind of superficial bias, and then for the negative, you usually even have a higher superficial bias. Basically, you see this kind of convex pattern. And note that here the y-axis is negative. So the negative signal for the bold post-stimulus undershoot is really highly dominated from the surface. For the positive, it's also dominated from the surface, but not as extremely as the negative. So basically, the slope over here is different than the slope over here. So the surface has really this huge component of the negative signal, which is maybe one of the most reproduced features in layer-dependent fMRI. All right, now that we have those tables, we can do statistics on them. And it can be sometimes tricky to do statistics on layer-dependent fMRI. You can do statistics across runs or across sessions or across different people. Maybe the tricky thing is that we have so many samples and they're not statistically independent. So the way how I do layer statistics is with the AFNI program PTA, which is shown in this file 07_statistics. The PTA program stands for Profile Tracking Analysis. It's a program developed from Gang Cheng, and it's basically implemented in R within AFNI. It's using the runs here as random effects and then estimating the layer profile. So it's basically fitting smooth splines and does not assume that the individual data points are statistically independent, but basically tries to estimate how independent they are, and then gives you p-values on whether two different conditions are the same or not. So we can see how this works. It takes two input files, a table of our data, and then the prediction as well. So here the table of our data would be having this kind of format. So for each condition, we have kind of the layer profile from 1 to 10, and then the individual values in there. And here I'm showing you examples from half of the runs versus the other half of the runs. It needs to have this format. But then also we need to have the prediction as well. For the prediction, you basically tell the program kind of what you want to have contrasted. And so here basically have my two conditions. This could be bold versus vaso, or it could be the early versus the late response, basically the positive versus the post-stimulus undershoot response. So we can execute this now. For that, we need to go into the layer statistics folder and then execute this single command. So it's looking at these tables, and then it's spitting out two files, a statistics file and a prediction file, those two. So in the statistics file, you can see the p-value of how likely it is that those two conditions actually are the same profiles, and the differences are just explained by noise. You can see the p-value is very, very low. So it's very unlikely that those are just explainable by noise. Then the prediction also gives you the smooth spline output in telling you kind of what the output would be for those two different conditions. And that's it. We have our p-value. So we went from the raw data at the beginning to the layer profiles and the comparison of the different layer profiles. Thank you.